Folks, thanks so much for joining us. We're really excited about today's webinar. This has been a long time in the making. We got a great team behind this project. We're really eager to share their details and to get folks' thoughts and hopefully future participation. So my name is Chris Neidl. I'm one of the co-founders of the OpenAir Collective. I'm a participant in this carbon forming mission. And what we want to do is share with you the progress of this project. It's an open source, do-it-yourself exploration into creative carbon removal that we've been working on in one shape or form for well over a year. But I think in this iteration, really since the beginning of this year. And what I'll do is, before introducing the core members of the team who are working on different parts of the project, and I'm going to share details, I just want to give you a little bit of background on OpenAir and how this project fits in to our overall community. I'm sure a number of the people that are on the call today are already members of OpenAir, but we are a all volunteer community that's focused on accelerating carbon removal or carbon dioxide removal. So that's the removal of carbon dioxide from the atmosphere, emissions that are already in the air. And for those of you who aren't familiar with carbon dioxide removal, there's sometimes confusion about exactly what that means, but this is a sort of a fancy official definition that we often use, which again, it's a series of various different types of activities that remove carbon from the atmosphere and then put it somewhere durably where it'll stay out of the air, either in geological formations, bioterrestrial formations, ocean reservoirs, or even in products, which is actually what we're technically talking about today. The subject of carbon dioxide removal is getting a lot more attention in recent years. This is because the science is now quite clear. The UN Intergovernmental Panel on Climate Change, in its last several assessment reports, has made clear that we really have to remove carbon dioxide from the atmosphere in addition to ceasing emissions and investing in adaptation to inevitable climate change. The ship has sort of already sailed on us not being able to do this as well as those other things. And we have to really start doing that right now, because if we want this to play a really significant role in future decades, that doesn't happen overnight. So we have to be advancing innovation and commercialization starting yesterday. And so OpenAir was formed as a community around the ideas of sort of mass participation in this effort. And it's really inspired by some classic open source principles. This is a famous quote from the open source thinker and practitioner, Eric Raymond: given enough eyeballs, all bugs are shallow. And that's really our belief. If we could bring in as many people to participate and directly contribute to new ideas and projects, we can actually play a really meaningful role in accelerating carbon dioxide removal. And so OpenAir is not a formal organization. We don't have a nonprofit status. We're a network. We're a bunch of people, increasingly from really all over the world, that hang out on the Discord platform, kind of like Slack, and a lot of Zoom calls every week, a lot of Google folders, GitHub, and we plan and execute different projects in a completely open, voluntary way. There's no formal staff. So again, we're distinct from a formal organization, and we behave and do different types of things compared to startups or government bodies or nonprofits. And some of the guiding principles, as I already mentioned, open source, the idea of the work that we do, let's reveal it to the world and have other people contribute, hack, tweak, and take it in different directions. And this is a category of what is sometimes referred to as peer production. So you have folks that largely on a voluntary basis are collaborating as peers to make exciting and interesting things happen. So we're an open source peer production community. We were founded, me and the other co-founder, Matt Parker, you'll see sometimes have different founding dates in mind. It kind of just organically took shape and people started to join. And then 2 years ago, we started our Discord, almost 2 years ago, exactly, a little bit longer. And that's when people really started to come in. And I sometimes think of that as our real founding. Again, all volunteer, all virtual. And now we're close to about 1,000 people who have signed up. We get about, 5 to 10 people join every day, and it increases all the time. And so the way that we function as a community is just with basic, widely available tools and platforms. As I mentioned, we're on Discord. We'll share the link to that for folks to be able to join. We typically have weekly or bi-weekly Zoom meetups where we really sort of talk about our projects and what we have to do to advance them. And as you'll see today, we also have a forum, which is a discourse forum, which allows people to, really share the work that they're doing in a more persistent type of way. so that we can actually grow our knowledge in a distributed way. So we'll be posting some of our forum links that hopefully we can get some of your brain power and ideas and perspectives involved with. OpenAir itself is roughly divided into what we call two different domains in terms of how we characterize the work we do. We have an advocacy wing. These are a lot of people that are working on writing policy and legislation and trying to get it introduced to advance carbon dioxide removal at the municipal, state, and now even national level. That's a very active part of your community. That's where I participate mostly. So if that's your thing, absolutely join, and we'll direct you to some of the many missions we have happening. And then the other one, which this project really relates to, is our R&D wing. And this is really our folks, people who are makers, tinkerers, people with PhDs, people without PhDs, that are actually coming up with things to make in the world, open source carbon dioxide removal projects. And that's what carbon forming really has evolved out of that wing. It's about half of our members are involved in the R&D. If you come into the OpenAir community, you'll hear this word a lot. It's not just a total free-for-all. It's really structured around specific goal-oriented projects that we want to have happen in the world, that have a sort of something that we want to specifically do or complete. And we call those missions. So carbon forming is kind of a super mission because it's sort of formed from some other missions in R&D. And the driving of missions, there's many different ways that people can participate based on their bandwidth and availability. But at the core of them, they're really driven by small groups, typically 5 to 10 members. I think our largest group we have is 12 members. And these are the people who show up week in, week out, and directly participate in advancing the project. And then sometimes we involve the much larger community to provide ideas and input. And one of the key things, as you look at this project in particular, it's important to bear in mind in terms of expectations. One of the things that creative networks do really well is what's called productification. So it means just trying to give rise to a new form that might not have a commercial value yet. It might not have a commercial pathway forward, but because we're not motivated yet by profit motive or customers or staff hiring, we can kind of think zany things and hopefully give rise to forms, products, ideas that then potentially could be the basis of commercialized products. This is where the personal computer came from. This is where 3D printing came from. And so we're trying to productify novel distributed forms of carbon dioxide removal. And so today we're going to be featuring a mission called carbon forming, which really involves 3 different R&D components that are being integrated together as we move forward with our team and hopefully with some of your help. This is a great team of people that meets up. You'll hear from some of them today. Some of them are backstage and some of them couldn't attend, but there's many different people all over the country and in multiple countries now that are contributing to it, some of which you're going to hear from today. This is a great picture of 2 folks you're going to hear from, Evan and Matt, who were at an Earth Day event this year featuring some of our R&D work. And so what you're going to hear from right now, I'm going to get off the stage and introduce you to some of the members of the team, is we're going to go over the pieces of the system right in a row. One is a miniature direct air carbon capture or DACC unit that was built by the community called Violet. You're going to hear about that. And then you're going to hear from 2 of our members about Cyan, which is a small off-the-shelf simple unit that actually converts calcium hydroxide into calcium carbonate, and in the process pulls carbon out of the air. And our direct air capture unit links up with that to accelerate that reaction. And then finally, there's the question of what do we do with it creatively? And you'll hear from one of our members, Evan. The point is to take that calcium carbonate and to actually add it into recipes with other ingredients into a filament for 3D printing. So the idea is taking carbon out of the air and ultimately printing cool stuff out of it. So that's what carbon forming is. And I'll mention that this is our instance of carbon forming, but we think of carbon forming kind of as a practice. So in addition to evolving this particular system that we're describing to you today, we hope as we grow, people with all sorts of other DIY carbon removal and utilization systems will participate in with their own versions of carbon forming. So with that, I'm going to hand it over to Matt Parker and XiaoYu Wu, who are 2 folks who are actively involved in the Violet project, and they're going to give us an overview of that component. Matt and XiaoYu.
Thanks so much, Chris. Great intro and great overview, and as always, a pleasure working with you. I'm excited to talk about some of the R&D side of OpenAir. We haven't done as much presenting on this as we have some of our advocacy work, so I'm really excited to introduce this to some people here today. Violet is our longest running R&D mission. And to sort of talk about it initially, I'm going to bring in one of our longstanding members on the Violet team, Professor XiaoYu Wu, who's a professor at University of Waterloo with expertise in thermal science, material engineering, and whose research focuses on development of sustainable technologies, and has been a core member of the Violet team for a long time now. So, XiaoYu. And next slide, please, Chris.
Sounds good. Thank you, Matt. Yes. So, hello, everyone. My name is XiaoYu Wu. I am a core member in the Violet project, working with Matt and other people. So when we think about Violet, we're mainly doing direct air carbon capture. So we call it DACC. And Matt later will tell you more about how DACC work. But first, I will give you a few background of DACC. So we are not the inventor of DACC. So there are actually a lot of several companies that are building this large-scale DACC plants, for example, Climeworks, and as well as Carbon Engineering. So here shows, on the slide, shows one of the projects, the project Orca from Climeworks. It started in September 2021, last year in Iceland. So you can see this is a picture from the large-scale DACC plants. They captures 4,000 tons of CO2 per year. So next slide, Chris. However, in our case, we're not building these large-scale plants. The reason is because, as Chris mentioning, we want to make this open source and we want to make this accessible to a lot of people. And accessible means that not only in material sourcing, but also in operating condition, safety, etc. So that is why we are focusing on this small-scale DACC machine. And the goal is that if we can capture 1 kilogram of CO2 per day at a cost under $2,000. So in this case, we want to involve more people both in developing this carbon removal technology as well as to educate people about DACC plants. Next slide, Chris. So for Violet, as Chris mentioned, that there are 3 different components for the carbon forming. And for Violet, we want to capture the CO2 from the air, so it will work as a CO2 concentrator to enrich the air going into Cyan. So in this case, we want to enrich the CO2 concentration, which is around 400 ppm in the air. We want to enrich it into around 4,000 ppm, so that we can give Cyan, the next machine, more higher concentration of CO2 to play with. So next, Matt will tell you about how it works, and then so give it back to you, Matt.
Yeah, so we're actually going to break out of the presentation for a second for a little bit of a live demo here. I am my day job is I'm a professor of game design at the NYU Game Center. So I built this little interactive to sort of show how direct air carbon capture works. And we're talking specifically about one form of direct air carbon capture, which is called moisture swing, there are different forms. So this differs a little bit from the versions of direct air carbon capture that you're familiar with. You might be familiar with a different form, such as electro swing or temperature swing. So this is a little interactive I built. I'm not a carbon removal expert for my day job, but a lot of what we do at OpenAir is trying to use our daily professional skills to help what we're doing here at OpenAir. So this little interactive shows how direct air carbon capture works with moisture swing. So air comes in that is heavy with CO2, the ambient air from around the world, and it goes into the machine. And inside the machine, there are several panels of what's called sorbent, chemical sorbents. These are chemicals that bond very strongly with CO2. And as the air gets exposed to it, it gets kind of pulled out of the air and attaches itself to these panels. Eventually, those panels get sort of saturated. The chemicals get as full of CO2 as they can hold. So we need to do something called regenerating them. And in moisture swing, what we do is you get them wet. You expose them to water or humidity in the air, and that breaks the bond that the CO2 has with it. So you do that at a specific time after it's captured all the CO2 it can, and you change where you're routing the air. So routing the air out into the world, you route it to somewhere where you can store it, and then you sort of suck it up there where you can use it for several different purposes. And in the case of carbon forming, for pumping into a cyan unit to mineralize it into something that we can use for creating physical objects later. And then the air comes out of the device with less CO2 than it went in, and it's a way of removing CO2 from the ambient air. So Chris, if we can go back to the slideshow, please. There we go. Just stop. Yeah, thank you. Next slide. Thank you. So this is the actual build of Violet. It was created by one of our members, Jeff Feddersen, in his home workshop. You can see that we're using like very everyday materials, but this is very much sort of the physical version of that interactive that I just showed. The air comes in the top, comes out the bottom. It passes through a block of a cartridge of chemical sorbents where the CO2 is supposed to bond with the chemicals in the middle. There's sprinklers on the top there. You can see from the diagram that when we're ready to, we can release the water and make it so that it's what we call desorbing or releasing the CO2. And then we have two different blast gates that we can open at the bottom for the air to flow out of. One of them we would have be the ambient air that we want to release out with less CO2 in it. One of them we'd want to hook up to a place, in this case, cyan, where we blow that air into to have the CO2 absorbed and mineralized for later printing purposes. So we are currently, like, this is a functional device that we have, but we are not nearly as efficient as we want to be. We have not reached that kilogram a day level. So we're continuing to do lots of experimenting and working with different chemicals, different preparation methods for those chemicals, different mechanical engineering solutions for exposing the sorbent to the air and getting the CO2 to blow off of it more rapidly so that we can get more cycles of CO2 removal as we go throughout the day. Chris is going to post a link to the Violet build log in the chat. And now XiaoYu is going to explain some of the chemistry we've been working with in an attempt to increase our effectiveness with Violet. So next slide, please, Chris.
Sounds good. Thanks, Matt. Yes, as Matt mentioned, that the core of this Violet machine is this CO2 bonding material. So this CO2 bonding materials mainly act as separation as the main purpose. They can grab the CO2 in air under some working condition, and then they can release it under another condition so that they can remove this CO2 from the air. And you can see that they come in different forms. On the left two figure, you can see that on the top left, you can see a flat sorbent material, which one of our member Dahl made it. Is based on activated carbon. And you can also see that on the bottom left, there are some beads, which is the ion exchange resins, which are usually used for water treatment. So you can see they are coming from different forms, and some of these materials, in order to make it to be able to bond the CO2, to capture the CO2, they might need to be activated. So some of the, or we can call it a preparation. And on the middle panel, you can see that there are one sheet on the top that is intact. But then after some incorrect preparation that we make it, we just broke it, right? So that is why we also need to experiment how we can prep these materials in a more efficient way, and also make sure that it's not breaking down the material. And once these materials are activated, we also want to test it to see if we scaled it up to put it into Violet, does it actually capture this 1 kilogram of CO2 per day as we wish? So that is why we also built a CO2 capture tester, a sorbent tester, that we measure how much CO2 is captured and also how much CO2 is released during different cycles. And So Matt will talk about how you can contribute to the Violet project on the next slide.
Thank you, XiaoYu. So yeah, we're looking to get as many people involved in Violet as possible. In order for something Violet to really work the way we want it to, as with most open hardware solutions, we need it to be not only effective, but we also need it to be affordable and accessible, something that people can do on their own. So we really want to like sit in the middle of this Venn diagram. Next slide, please. I want to be clear about something. You don't have to be an expert in any of these things to contribute to this project. I am not very good at chemistry. It was my worst class in high school. I only ever took chemistry in high school. But we have members like XiaoYu, Dahl, lots of people who are experts who can help, and I am able to follow their instructions and run a lot of these experiments. So what you're looking at now, these are experiments that I have actually run in my apartment in terms of making Violet more effective. So, you know, the middle one is me prepping with some of the chemicals we're working with. That's amberlite bromide, but I'm working with sodium carbonate to prepare it for chemical bonding, which is basically the main ingredient in most detergents. You know, most labs have much more fancy equipment. I'm using a milk bag for making like almond milk to contain the sorbent in this bag inside of a normal cooking pot with something that is a stir meant for stirring soups. These are all like sort of very low-grade versions of what you get in a fancy lab. I'm using on the left, there is a picture of a chloride tester that I'm testing samples of that water to see if I remove the chlorine effectively from the chemicals I'm looking to chemically prep. And on the right side, that's one of our sorbent testers, which is a very basic setup with a microcontroller, a CO2 sensor inside of a food container hooked up to my computer so that I can measure the CO2 levels rising as I wet the sorbent inside of the container and see how much CO2 that we're getting released from the sorbents that we're using it. So yeah, anyone can contribute to this if you're, you know, have the interest and willingness to participate. So next slide, Chris, please. So yeah, these are just some of the questions that we're working on right now. And we have a public forum that you can look at some of the experiments we're doing, some of our findings, our successes and failures. We try to post everything there to help people. Some of the most useful things we've actually had in Violet development is some of our failures that we've talked to other institutions about when they're trying to build their own open source hardware, direct air carbon capture machines. They've learned from some of the mistakes we made, and so they don't have to go down those roads. We try to prune the possibility tree. So these are some of the big questions we're thinking about now is how do we chemically prep large volumes of sorbent? When I'm doing them in my apartment, I'm usually working with about 10 grams of sorbent at a time, but we're going to need to prep kilograms of sorbent. What are the best ways we can do that outside of a lab or factory setting? Are there other materials we should be looking at for sorbents or other materials we should be looking at sorbent preparation? We just started to experiment with sodium phosphate instead of sodium carbonate for prepping our sorbents. And so far the results aren't great, but we still have more to do, more things to try. And that's what we do at OpenAir. We keep trying and talking to experts and trying to figure out what the best possible approach is. And yeah, how do we, if you're somebody who's less on the chemistry side and more interested in sort of the mechanical engineering side, or someone who's an electrical engineer, how do we produce maximum airflow through this for the minimum amount of electricity? Because when you're dealing with carbon removal, it's always important to think about how much energy you're using to make this happen, and how can you get the most bang for your buck in terms of electrical consumption. So with that, I'm going to turn it over to the next section of carbon forming, which is our carbon mineralization unit, Cyan. So Dahl and Edward, it's all yours.
Great. And if I could just intervene with a tiny bit of housekeeping that I didn't mention, please, if you have questions, submit them in the Q&A. And if we do run out of time, that's what the forum is for, and that's what joining OpenAir is for. So this is an ongoing discussion. And I should also say, Matt Parker is one of the co-founders of OpenAir. He's based in Manhattan. And XiaoYu is a chemical engineer who is a professor at the University of Waterloo. Matt is a professor of game design. So if I could just ask Dahl and Edward to also say where you're from and what you do during the day to give people a sense of how diverse this group is.
Thank you very much, Chris. Thank you, Matt, for an excellent overview of Violent. My name is Dahl Winters, and I'm in Evergreen, Colorado. My day job is actually to run my company, Deep Science Limited, through which we kind of developed an idea, a concept for that became Cyan, which we wanted to open source and make something available and accessible to a broader audience. So Cyan developed as an open source OpenAir mission around carbon mineralization. And what that means is, as Chris described earlier, it is the act of taking a material called calcium hydroxide, which likes to bind with CO2 under humid conditions. And so when there's CO2 in the air and you have that calcium hydroxide powder, you get calcium carbonate, which is a mineralized long-term storage form of CO2. The whole point of Cyan is to provide a reservoir for that CO2, and it's something that's very low cost. It can be built under $40. It's something that is relatively simple to build. What you see the picture here of can be built within a matter of 2 hours or so, or less, depending on what components you use. What we're going to talk about today, Edward and I, are facets of how Cyan developed. And definitely, if we go to the next slide, we'll outline the goals, as well as some current developments that are occurring within Cyan. So our goals have been to demonstrate microscale carbon removal with a simple low-cost system. By microscale, I mean that we're taking very small quantities of CO2 out of the air to make this accessible to a wide range of audiences. People can do this in schools, in laboratories, even at home, which is where I do a lot of my work. In order to demonstrate this, we basically build this unit, and we have the instructions available on GitHub to be able to build your own. There's also GitBook instructions, which might get posted in the chat in a little bit. But basically, this is something to introduce people to the idea, the concept of carbon removal. That allows companies that are bigger and have larger units to gain more support and become more effective in the fight against climate change. Next slide, please. So CO2 is stored in inert form, and I use the term calcium carbonate, but we all know that that's a high-tech term, but it's essentially seashells. It's a natural form of carbon storage, and it lasts for thousands of years. And it also has a lot of downstream uses, which we're going to get into in a bit, showing you what can be built from calcium carbonate, from the carbon that's in the air. Next slide, please. Lastly, a major component of what we want to focus on with your help is to measure and report the CO2 removed. We have a number of talented people here within OpenAir who do electronics engineering, David Wilson and Jay Moriali. They have been pioneering techniques to do more than just weigh the product, which is how we've been measuring CO2 up until this point, the CO2 taken up. We want to definitely look into electronic methods of doing that, automated methods. So with your help, we can possibly do this, please. I think that I'm going to turn this over to Edward to talk a little bit more about the different innovations that have occurred that he has actually taken upon himself to do. So Edward, if you'd like to continue, and hand it back to me afterward.
Okay, thanks, Dahl. So I'm in Des Moines, Iowa. I come to it as a maker. I work in the sculpture department at Drake University, and I have no real science background. I just like to build things. So when I first started, we had to connect Cyan to Violet. So I started to try to figure out how to increase the CO2 atmosphere and then create pressure. So that was pretty much my initial direction. That's kind of what I've been working on. If you can go to the next slide, please. And so initially I just started with a soda stream, which was a suggestion from Chris, actually, and it worked. It showed an increase, but at a much lower rate, at a much shorter time span. However, soda stream canisters are really expensive, so I moved to a CO2 canister for beer brewing and began to utilize that method and to see what would work. One of the hardest parts that I found is just containing the CO2 with no leaks, and then also increasing humidity. At a certain point, I've decided that to increase the calcium hydroxide connection to the ambient air and carbon, it needed to be agitated and possibly air suspended. So I started to inject it with some forced air. And the next slide, please, which you can see on the left. And that, of course, opened up a lot of other problems. Backflow, it needs a filter. The calcium hydroxide kind of pools in certain areas. So I'm currently working on different directions of air input, from cyclonic to this upper section here. If you see the airflow in the top kind of blower fan goes through an upper chamber and goes through kind of like a little venturi tube to suck through what would be a CO2 kind of enriched area down into what's a peanut butter jar, essentially. And then at a certain point, I'm trying to get that to become a cyclical instrument so that the backflow circles back around into the air input of the fan. But of course, that's becoming more and more difficult. And then on the right, you'll see a tumbler, kind of a rock tumbler method, which works pretty well. However, I don't know right now how to put more pressure into it. And that becomes a bit more of an issue on that end. So that's kind of where I'm at this point. Any help would be good. Like I said, I don't have any real science backgrounds other than a little bit in college and in high school. I just kind of like to make things. So the more help, the better. Dahl, I'll hand that back to you.
Thank you very much, Edward, and appreciate your help in making this project, extending it, and all of your work. I wanted to briefly go over 2 more slides. Improving the CO2 measurement methods. David Wilson has done excellent work in what I described earlier, the electronic measurement of CO2. So any of you who are electronics experts, or even if you're just interested in dabbling a little bit, we could use your input on what we're developing. This is a method using electrical conductivity to try to see how much CO2 has been removed. We know that if we take a dissolved amount of calcium hydroxide, it has a certain electrical conductivity at certain pH levels. If we take a sample of our product, we're going to get a different curve. How do we determine the difference between those curves and get CO2 measurements from that? That's basically the goal of this. And if we go to the next slide, please. We also have been doing IoT and cloud reporting of those CO2 measurements. I developed some code for Dev Network hackathon to transmit data from a CO2 sensor to a cell phone that connects to the cloud, and then outputs that information to a web app, which is currently, it's not at that particular URL anymore, but I certainly have the code available on my GitHub if anyone's interested in extending that. It's totally free. To the forum, I wanted to also make a mention very briefly of the need to, given how difficult it is for us to remove carbon from the air at large scale, we really need to focus on reducing our emissions as much as possible. We're never going to get all 39 or 40 gigatons out of the atmosphere with CBR, but we are going to do that as much as we can because we need all people, everyone to be able to help on this fight. So I'm going to go to the next slide, and then this will be my last one for the section. This is where we could use the most help right now. Basically, how can we measure that CO2 efficiently? This would open up a huge amount of exploration amongst the open source community to be able to judge how much CO2 they're taking up with their devices quickly and at large concentrations of calcium hydroxide. And finally, could we connect many cyans together to a violet unit, for example, or maybe even a really big cyan to an even bigger violet unit? Basically, we need to do more to understand how we can connect these systems together. And that's a topic for another day. when you join OpenAir. But now I'd like to hand it to the carbon forming third section, those who have been doing carbon utilization in products. Evan has been doing excellent work. I'll hand it to you now. And thank you so much, everyone.
Thanks, Dahl. So my name is Evan Landau. I'm a freelance industrial designer and researcher based in New York City. And I've been working on this third section of this chain, which we're calling carbon printing. And the idea for carbon printing came about because we were imagining the situation where DACC as an industry or a discipline has been scaling up very rapidly, as Chris was mentioning before. And it's this idea that, okay, we're removing all of this material from the air in different ways, and are we just going to be sitting on an incredible amount of carbon dioxide and materials like calcium carbonate and not really know what to do with them? And that's, of course, a bit of a generalization. There's, of course, a lot of great work being done with sequestering CO2 in concrete, which is very important. But I, as an industrial designer, someone who designs and manufactures products, I was thinking, can these small things that we use every day that are everywhere, can these be places to store carbon dioxide from the air? And at scale, can that be part of the puzzle piece, or a piece of the puzzle to add up to that 40 gigatons? So this phase of our project is in the pretty early stages of R&D, and what we're doing so far is just figuring out ways to take the calcium carbonate that we're creating with Cyan and put it into a form that's more useful to create objects. And I'll go through a couple examples of that. So Chris, go to the next slide. This in general is the system that have been conducting these material exploration trials. We're taking the material from carbon removal systems, and this machine that you see that was on the last slide too, it's a filament extruder. So it's basically just a mini desktop injection molding machine, and you put material in the hopper, and there it's granules of PLA and Pen 100, which is a plasticized version of, or plasticized form of biochar or fly ash made in a reactor. And that's extruded at a couple hundred degrees, and it comes out as a filament. And that filament is the standard size for your typical FDM 3D printer. I have a Creality Ender 3, and I use that to create objects like I'm showing here, material things that are proofs of concept, really, for ways to create mass producible products. And all of the material explorations I'm evaluating, similarly to some other folks on this panel, I don't have much of a science background. I have a background in mechanical engineering and design, but I'm evaluating these materials for their properties and functionalities to be consumer products, like durability, waterproof, you name it. Think about the things that you use in day-to-day life. So we can go on to the next slide here as well. This is getting a little bit more specific into the types of materials we've been trying out. And on the questions I have on my last slide, it's open-ended. We're definitely looking, as I said, this is really in its early stages, and anything that I can stick in that extruder or mold in a toaster oven in my backyard, better. We're trying to find things that have legs to develop and scale up. And so some of the carbon-based materials I've been using, Pen 100, as I mentioned, that it creates this black filament, calcium carbonate from Cyan, and really anything else that can store CO2 from the air in a physical form. Some of the bonding agents or the other materials that I'm using to sequester the carbon dioxide are PLA, which this is partly made from. These filaments here are part ABS, so what they make Legos out of, and calcium carbonate. PETG I've used, and then I'll show some experiments using resins. But I'm particularly interested in finding some kind of polymer or bioresin that can be used to make these things a little bit less plasticky while still having those material properties that we like to see. Some of the forming methods I've been using: extrusion, 3D printing, casting and thermoforming. And we're interested in, if anyone has any experience in the 3D printing industry, we're interested in finding ways to have a direct pellet feed, finding some DIY plans for creating a direct pellet feed into 3D printers to avoid the whole extrusion process. As you might know, carbon makes things brittle. You're talking about something that's 1.75 millimeters in diameter. That presents some problems, obviously, which has led us to casting experiments. But really, what we're talking about here, what I'm trying to do is create everyday products as carbon storage at scale. And the goal there being mass manufacturing, or creating proofs of concept for mass manufacturing. All right, go to the next slide, please. So these are some experiments I've done with Pen 100 as filaments. It's the other half of it. It's about half to 3/4 Pen 100. And in these cases, I believe these are all made with PLA as well as the remainder. But you'll see a plant tray, a CDRLA sponsor trophy prototype, and a little man that we affectionately call Carbon Man that was made with a 3D printing pen. And while these things are not consumer, on the shelf ready, again, they're trials that prove the durability and really practicality of using these materials in everyday products. We go on to the next one. And so these are some of the initial, and this is something that we've been working on for a bit shorter of a time. So there's obviously a lot of exploration to be done here, but these are examples of using calcium carbonate mixed with PLA on the left-hand side. And this is something I just did in my backyard in toaster oven with a little bit of pressure from a bottle and a tinfoil mold. So really scrappy, really ad hoc, but showing that with some heat and time and pressure, you can combine as much as a third by weight calcium carbonate with PLA and have something that results in an object that's durable, doesn't have any real brittleness to note. It can be machined. I put on a drill press, or I put on a drill press and a bandsaw, so has the ability to be formed in secondary processes and really does a good job of capturing that at low heat and pressure. And so thinking about how that relates to something like an industrial heat press or vulcanizing materials. And then on the right, that's an example of a little more than half actually calcium carbonate and epoxy resin, which made a really nice butter looking block of material that also took to machining very well and has a lot of potential. I, as a sustainability advocate and an industrial designer, I'm well aware of the negatives of using materials like epoxy resin, but these are the initial steps, and hopefully we can find through other members of the community and additional research materials that both have the properties that we desire, but also are a little bit lighter on the environment. The flip side to that, though, is I've done a lot of research in using waste materials as starting points for products, but this is kind of an interesting case because really we want these things to be as non-degradable as possible. We're trying to lock these materials away for as long as possible to keep it out of the air. So it's kind of this, it's almost a bit of a paradox, and it's kind of the opposite of many of the initiatives I've been on with sustainable materials and alternative materials. So if you go on the next slide now, I think these were just the questions, but so the open questions, I've posited these already, but are there any other solid carbon-based materials we can use in these trials? Or are there any other bonding agents that we can use to replace plastics and resins, particularly bioresins? And are there any other methods of material forming that we can do in at home trials that have parallels to mass manufacturing. And so would love to talk about these. There's a discourse channel for these experiments as well. And yeah, that's it from me. So I think we're gonna open it up to Q&A now.
Fantastic. Thank you, team. That was excellent. So we can go ahead and do some Q&A, and just a couple of things to really stress here is, we only have 13 minutes left, but this is the beginning of a conversation, hopefully with all of you. I know that Greg and Jay posted relevant links based on what was being described, the forum links for posts about each of the three pieces. So it's an opportunity for you to just directly go there, share your thoughts, ideas, and questions. And then we'll also, if Greg or Jay or someone else can also just drop the OpenAir join link, we can let you into our Discord, and that's where we just have an active ongoing conversation. So really look forward to people's input and participation on any level, whether it's sharing an idea or becoming part of our core group. So I'll just start with that. Let's take a look here at the Q&A, and we'll just sort of field it with the group here. I think a number of them were answered, but let's go ahead and start with one that comes in for Evan from Bill Gilmore. Evan, any chance of making something that could be used for constructing even minimal housing for homeless people? And let me just say quickly before you answer, I was on a call with a member in Eugene, Oregon the other day who let me know about a town in Oregon, which is called, oh my God, I'm forgetting it. I'll look it up. John something, Oregon, where they actually are doing that. They're building affordable housing with 3D printed concrete. So I was extremely interested in the possibility of using calcium carbonate sourced from the air as an aggregate for projects like that. So anyway, that's very, very cool. But Evan, any thoughts on that? Oh, I think you're on mute.
I was going to say something along similar lines. Actually, I've done a lot of research into 3D printing houses, and I think that there's a lot of overlap with that and all the efforts that have been done in creating carbon sequestering concrete. And so I think the connection of those two worlds would be a really exciting opportunity. I'm not sure that any 3D printed housing development has utilized that concrete like that, but I think that would be a great opportunity. As far as the materials that I'm working on, they're focused, at least for the time being, on smaller scale objects, but I definitely see the potential in scaling that up. But for now, I'm leaving that to the folks working hard on carbon negative concrete.
Yep, great. And well, this is a question to Evan, but I think it applies more broadly to every single phase of this project. It's from Ann Pasick. And have you given any thoughts to the life cycle analysis for your additives? I get this is definitely not the first priority in product development cycle, but I wonder to what extent these products can potentially be described as carbon negative. I think you're right. We want to start with the instantiation of this, but life cycle analysis is going to be a key metric for us as we go forward, what the energy use, the materials, and we want to find out cheap open source ways of actually measuring that. So we'd love your help on that, Ann. But Evan, if you have some thoughts, and maybe the other members can speak to that for their components of the project as well.
Yeah, I'm thinking about this along similar lines as well. I kind of liken it to electric cars. There's the naysayers of electric vehicles talk about how many of, in many cases, the batteries that drive electric cars are powered with fossil fuels. And while that may be true, it represents progress, and you need to make incremental progress in order to then optimize it, and have it be in a closed loop with a more sustainable life cycle. And I think that these trials that we're working on definitely fall into that category. One of the really important things we need to do with these materials, once something that has a bit of legs has been developed, is analyze this really carefully and see how much energy are we using in the extruder, in the printer, how much energy is it to pelletize these materials, where are they coming from, what are the carbon emissions of it getting to my doorstep. And all of these things need to be considered, because we can't say something is carbon negative or neutral if me running this thing in my basement at 500 degrees Fahrenheit for a couple hours is going to totally negate all of that. but yes, still very much in the experimentation phase, and that is something we're definitely keeping in mind.
And help us figure that out.
Sorry, just quickly on the violet side, part of the reason we chose moisture swing over other technologies is the hope that we can have it be passive at some point and not need these huge fans blowing through it to capture CO2. But currently, we have huge fans blowing through it to capture CO2. So that's definitely something that, thinking about what the goal is, even if it takes steps along the way that are not, truly carbon negative, we're working towards that, and we need to increase the effectiveness. As part of the reason why we're experimenting with so many different chemicals and trying to up our efficiency to make it so that the juice is worth the squeeze.
Great. Any other thoughts, Dahl, just on the life cycle question? It's obviously an active subject within our community. I don't know if you had anything to add to that.
Yeah, the life cycle analysis for the various components that can go into like whether or not it's 3D printing or so. If that was the question, I do have some information on that. Basically, we need to conduct to actually read the LCA literature as the next step to try to isolate what components are really carbon negative and what's not. Biochar is carbon negative. Calcium carbonate, obviously, depending on where it comes from. If it comes from cement or even calcium hydroxide, the way it's currently made, it won't be carbon negative. But there are low carbon forms of calcium carbonate coming online, like through several companies. So in the future, we are going to take that into account, but we need more help in assessing the literature. If anyone is able to contribute that to our collective, that would be really great.
Great, and I just posted in the link. We have a great new show that two of our members, Harsh and Charles, started called CDR Horizons. It's a YouTube only show, so definitely click on that, watch, and subscribe. But we had our first episode was with a kind of a world leading expert on moisture swing. So that's a good deep dive into moisture swing DACC. Dahl is going to be actually on the show soon talking about a paper she's getting published about biochar and concrete utilization. And I think a lot of the subjects, we have one planned for calcium carbonate in 3D printing soon. So a lot of the subjects discussed there will be deep dives with academics about subjects that are related to carbon forming. So definitely check that out. Just a couple of other questions. This is one from Eric Foreman. Is there a visualization somewhere of cubic volume of C-carb that might be produced by one machine, quote unquote, chain in 1 month at its current prototype stage? I won't even pretend to understand that as a non-designer, but I don't know if anybody has anything intelligence to respond with for Eric's question.
Curious if this is the Eric Foreman that I know, but I'm sure there's more than one. I think we don't have a visualization of that. Does anyone made a visualization of?
There's a visualization I can pop into the chat. This is made by Real World Visuals. I just happened to think of it during our talk today. This is an awesome visualization of how much CO2 we actually need to remove in a certain period of time. And you can watch the video. There's different explanations of what a ton of CO2 looks like, what a city block of CO2 looks like. And it's pretty amazing, that video that you'll see on that page. We need to get to that scale. It's not going to be just our solution that will get to that scale. It's going to be our solution promoting the growth and the idea exchange and the education and the ability of people to interact to get to that scale. So we're trying to, and we're being pretty successful at starting a conversation around carbon removal. And with the help of people like yourselves, we can definitely get there. But that picture, just take a look at that picture and look at that video all the way through, and you'll begin to understand the immensity of what a gigaton looks like. And that's all we want to do, is to help out others, to encourage others to grow and to be able to seed the future growth of carbon dioxide removal. So.
Great. Just a couple of things to add too. I was so happy, Bob Wright. I'm glad you turned up. He's our member from Eugene, Oregon. He mentioned it's John Day, Oregon. He might have a post there. That's the town that's doing 3D printing concrete for affordable housing. I also want to say, for those of you from the open source hardware community joining us, Dahl's Cyan design is actually the first product generated from the OpenAir community that has the Open Source Hardware Association certification. So I don't know, Dahl, if you even have a link for that, you can drop in, but that was a proud moment for us. So we have another question here from Mike Robinson, another awesome member based in the Seattle area. He says, Evan, have you considered focusing on carbon negative polymers rather than incorporating carbonate minerals? Capturing CO2 can be combined with green hydrogen to create polymers that are made from captured carbon rather than from fossil carbon.
Yeah, I think that's actually one of, in my humble opinion, one of the best uses for gaseous CO2 that's removed from the air. And in a perfect world, I would love to make these filaments out of both. So have that carbon negative polymer, and then also be able to utilize physical carbon as well. And, talking about doing analyses and crunching the numbers on these, maybe one over the other is just more inefficient. And I think that's some data that I would love to get on hand and explore. So yeah, but it's only, I think, through the exploration of these materials that we can really determine that. And carbon does a lot of amazing things for, it turns iron into steel. So maybe there's actually properties through actually adding something like calcium carbonate to these polymers that can increase the material properties that we like in products. There's also, if I could tack on an answer to the anonymous attendee,
I was just about to
ask the question about the CO2-based filament. The main problem, as I mentioned before, is that it makes it very brittle. So it has the tendency to snap. I haven't found so far. I mean, I've left these things out in the rain. They seem to be just as water resistant as plastic is. So I haven't really found any difficulties there. But the main thing really is the reduction in pliability and shear strength.
Great. And we're just at time now. I just want to also flag that one of the folks who's joining had really interesting ideas around graphene. And I just want to point you, if you go to our YouTube channel, there's a company, we have a show called This is CDR every Tuesday, which features different CDR entrepreneurs talking about their solutions. There's a company called Mars Materials that is actually working on an alternate way to create graphene in carbon fiber that might be of interest to you. So you can go ahead and take a look at that. And they're actually in our Discord as well, that company. So we'll go ahead and close right now. We're at the hour. This has been amazing. I just want to really stress, this is the beginning, and we're kind of always going to be at the beginning. And the quote I said about, with enough eyeballs, all bugs are shallow. And we really mean it, that anybody with any kind of expertise or passion for anything can contribute. Even someone like me who hasn't taken a science class since senior year in high school. The role of writing about this, spreading the word about it, getting more people involved is a core piece of what we have to do. So even if you don't have that background, you could be a participant. But if you saw something that raised a question or gave you an idea, whether it's about a gigabot, which I don't know what that is, but I see Mike Parker posted that, it might be Matt's brother, please do share it. Join our Discord and post on the forum and be a part of this. And let's really make carbon forming a thing. So I want to thank all of these awesome members of the team who are so fun to get to know and see them produce. And hopefully some of you will join the effort. So with that, we can wrap up, and you'll be getting a video of this. I'll be sending it out either later today or tomorrow morning. Please watch, share, repost, and join. Thanks, everybody.